Good afternoon, students. So today we will discuss about the BJT. BJT means bipolar junction transistor. Bipolar junction transistor. So here the transistor, which is a three-layer semiconducting device. That means which is consisting of either two N and 1p layers of materials, or else 2p and 1n type of layers of materials. So this is the form which is called an NPN, or else other one is the PNP transistor. So there are two types of BJTs, bipolar junction transistors, PNP transistor, NPN transistor. What do you mean by transistor? Means here trans plus isters, transmitting the signal using the resistors from one to other place. So the transistor types are BJTs, bipolar junction transistors, are bi means two. Okay, so either current conduction maybe takes place due to the positive holes or else negative electrons. So that's why you can call it as here in two way the conduction is going to be takes place. That's why it is BJT here. So the symbolic representation, or else in construction purpose, if you want to observe the PNP or else NPN, so you can see that here NPN transistor or else PNP transistor. So the left hand side portion is emitter, which is base, collector, emitter, base, collector. Okay. So the transistor which is having three portions. So LHS is the emitter, right hand side is the collector, and middle portion is the base. So there are two junctions. Where is that two junctions? Here is a one junction, first one, and this is the another junction. Two junctions. This is one junction diode. Okay. First junction diode. This is another junction diode. Is it clear? So that the two junction diodes are there. So there are two junctions. So the transistor can be considered as two diodes. Two diodes, which is connected back to back. First diode is this one. Second diode is this one. So how many layers are there? There three terminals are there. Middle section is very thin compared to the other one. Okay. How the naming of transistor terminals is given here. That means the transistor has a three section of doped semiconductor. The section one side, left hand side, which is called as emitter, and the right hand side section called as a collector. Middle portion is called base. So here the symbolic representation of the transistor which is going to be giving out, you can observe that current which is coming out from the base to the emitter. Base to the emitter. This is NPN transistor. When the current is coming out from the emitter to the base, PNP transistor. Okay, so this is the case. So emitter, if you know this, you can easily write it down. The section of the one side that supply carriers, either positive holes or negative electrons, which is called emitter. So emitter shape region which is always forward bias with respect to the base so that it can supply carriers. Whereas for NPN transistor, emitter supply holes to its junction. Emitter supply positive holes to the junction. Whereas for PNP transistor, electrons which may supplies to its junction. Next is the collector. The right hand side section of the transistor which is a collector here, which is always in reverse bias with respect to the phase. Emitter which is always in forward bias. Collector which is always in reverse bias. And NPN transistor which may collect the collector receives the holes which are coming out from the base to its junction, whereas PNP transistor which collector receives electrons which are coming out from base. So middle portion which is very thin between the two p-n junction diode, that is called here base. So what are the important factors to be remembered here? Transistor has three region, emitter base collector. Base is much thinner than the other emitter and collector. Emitter is heavily doped, always in forward bias. And the role means here which injects the large amount of carriers towards the base. And base is lightly doped, which can pass most of the carriers and towards the collector here. Collector is moderately doped. And the junction between the emitter base is called emitter diode, and the collector to base which is called collector diode. That means how many diodes are there? Two diodes, emitter diode and collector diode. Emitter diode which is always in forward bias, and the collector diode is in reverse bias. So the resistance of emitter diode is very small, and for collector diode is very high. So if it is small means which is in forward bias, if it is high means it is reverse bias. You can see here working of NPN, but actually which is not in our syllabus, but you need to know that here NPN transistor, how it is going to be working out, and PNP transistor, right and left hand side is a positive holes are there. Middle section N means minority charge carriers, negative electrons are there. So symbolic representation of the transistor. That means here common base configuration. Base is common for input as well as output. Then the type of configuration is called common base. Common configurations are three type: common emitter, common base, and common collector. If it is the base is common for input as well as output, common base. Collector is in common for input and output, common collector. Emitter is common for input and output, common emitter. Okay. So that the emitter to the base means toward the charge carries arrow mark, which is going to be indicating that emitter current which is passing towards the base means PNP transistor. Okay, arrow mark. Which is in reverse bias means NPN. So what is active mode, saturation, cutoff mode? Emitter base junction, which is always in forward, base collector which is always in reverse bias. That you can call it as a active mode. Saturation mode means base emitter junction which is forward and base collector junction is also forward, saturation. Both these two are in forward bias, then that is called saturation. What is cutoff? Both are in reverse bias, cutoff mode. Please remember these words. So transistor can be connected in a circuit in the following three ways: common base, common emitter, common collector. So you can see that base is common for input as well as the output. So this is for NPN transistor, this is a PNP transistor. Okay. Which one is NPN? This is NPN. This is PNP. Now, because of current which is moving toward the base, here from base to emitter. Here a signal is there. Signal means you can see the circuit. How do you connect this means here? A signal is there. Signal means AC. Fluctuations are there. Input AC, whenever AC is which is connected into the circuit, there is up and down fluctuations. No constant current or voltage is to be fed through the transistor or whatever the component equipment component is to be used in the circuit. Here a DC supply, plus and minus. Okay, a DC supply is to be considered. That means you need to say that here, which is always in forward bias. House R means a positive terminal of the battery which is connected to the P region. Na? Why? Because of what type of transistor it is? PNP. Structural. So positive holes, positive terminal. Then which is negative. Collector base which is always in negative. That means which is in active mode. Okay. So here positive which is connected to the negative. So that which is in reverse bias, which is in forward bias. So that what are the conditions we have been discussed here that you need to implement. Then only the circuit which may constitute the current across the load. Okay. Here also, this is NPN. NPN means negative, here negative, forward bias. This is positive, negative, reverse bias. Okay. So, here base is common for both input as well as the output. Then this configuration is common base for NPN as well as PNP transistor. So due to the DC in emitter region which may have emitter current IE for base, due to the majority charge carriers, IE is generated, and due to the minority charge carriers, very small amount of current which is may be constituted at the base region, that is IB, and remaining whatever which is coming out from the emitter region towards the base, and the base which is feeding all these carriers towards the collector region across the collector diode junction. So that here collector region which may be having such a current, that is IC, collector current. So here a load is to be considered. In collector region, the load resistance is RC. C means collector, R means resistor. Okay. So across this we are taking output. But what about the signal? Signal is also. So amplification factor for this common base is alpha. So what do you mean by here? You can see a delta which is indicating here change in current I. So change in the ratio of the change in collector current to the emitter current change. You must so okay. The ratio of the change in collector current to the emitter current is nothing but a amplification factor for common base. At collector to base, voltage must be constant. And the alpha value which is less than the unity The range is 0.9 to 0.99. Next, expression for collector current. So here the emitter current does not reach the collector terminal because of a small portion of its constituted base current. So I E equals to emitter current equals to the sum of the collector current and base current, IC plus IB. So as we know that basics, that is a collector diode which is always in reverse bias. So here for a very few minority charge carriers which may passes through the collector base junction, and this should be constituted the leakage current, that is ICBO. Collector to base with emitter open, CBO. Collector to base with emitter open. Open means no current which is constituted at input section. So that here base to collector, how the current which is to be constituted, that is ICBO. We have ICBO which is due to minority. Okay, minority charge carriers. So the collector current constituted a portion of emitter current, that is C equals to alpha E, and also leakage current due to the minority ICBO. So that what is the total collector current? IC equals to alpha E plus ICBO. Here IC equals to alpha into IE means IC plus IB plus IC. Okay. What is this? Actually, IC equals to alpha IE plus ICBO. IE means IC plus IB. So here IC is there, here also alpha IC. So that if you are taking to the left side, IC minus alpha IC equals to alpha IB plus ICB. So if you common the IC, 1 minus alpha, same thing. So IC equals to alpha by 1 minus alpha into IB plus ICB by 1 minus alpha. So what are the characteristics of common base? Common base voltage, if you are going to be changing here, 1 volts, 10 volts, 20 volts. So what is the base to emitter voltage, and what is here emitter current? Okay, base emitter voltage versus emitter current. So the emitter current which may increases rapidly with the base emitter voltage. Why? Because of here input resistance is very small. So emitter current almost independent of the VCB. Okay. Next. This is the common base configuration output characteristics. You are getting a constant volt current, constant current here in the cutoff region and the active region. So input resistance, output resistance. Common emitter. Emitter is common for input and output, both. Here is the amplification factor beta. So the change in the collector current to the ratio of the change in the collector current to the base current, and delta IC by IB, which is amplification factor. What is the relation between alpha and beta? Alpha is delta IC by delta IE. Beta is delta IC by delta IB. You know pretty well IE equals to IB plus IC. Delta, if you put a delta here, the same thing. Then IC minus IB. Then beta value, delta IC by IB is delta E minus delta EC. So beta value should be calculated, and that maybe gives you here alpha by 1 minus alpha. Next expression for collector current. This is beta. So you know pretty well in previous section common base alpha E plus ICBU basic equation. Substituting here same IB by 1 minus alpha plus ICBU by 1 minus alpha. So what are the characteristics? If you're changing the collector emitter voltage 20 volts, 30 volts, 40 volts, like that you have. So input resistance out. Next, last one is the common collector configuration. Collector is common for input and output. Common. This is gamma amplification factor. What do you mean by gamma? Means the ratio of the change in the emitter current to the base current. So the same gain is to be produced in the case of CE. So gamma value. So beta value alpha by 1 minus alpha. Comparison. Input resistance, output resistance, voltage gain, applications, current gain. For common base, common emitter, common collector. These are the values. Next, transistor is an amplifier. How the transistor may work as an amplifier. Most important short question. Signal is there, AC signal which may fed through this. So what type of configuration which is CE, common emitter? Why? Because of emitter is common for input and output. Here, input, output. Input forward, output reverse. So that IC current value, how it is going to be giving out, which is NPN transistor, and where battery VBB which is connected for NPN transistor. So battery VBB which is always connected with the base in order to make base forward bias. Regardless input as AC power. Next is the output take a load resistance, capital R. So during positive half cycle, input of AC already current will keep the emitter base junction and more forward bias. So more carriers will be emitted by the emitter, and huge current will flow through the load resistance. We can find out the amplified signal. Amplification, strengthening the signal. Low may be considered as a high signal, that is amplified. Next, during the negative cycle, input AC will keep the emitter base junction is less forward bias, so that the less carrier will be emitted by the emitter, hence the collector current decreases. So which may results the decreased output voltage. So which is a CE configuration for NPN transistor. Next, battery EBV, which is connected with the base in order to make base forward bias regardless of input AC. Next, where the output which is taken across the loaders. Okay, so transistor circuit analysis, it is necessary to determine collector current for various collector emitter voltage. One method we can determine the collector current and integer value. So more conveniently, we can use a load line analysis to determine the operating point. So this is the equation part. So for common emitter NPN transistor, here there is no signal at all. By applying the Kirchhoff voltage law in the output section. So operating point, the zero signal values of collector current and VC, which are known as the operating point. So this ends our common configurations. Again, I will show you. So we have been discussed all this. Transistor configuration and characteristics. So biasing, what is NPN, what is PNP? Just now, through these slides, we have been discussed. Common configuration. Here you can able to observe that signal DC supply across the load. So bipolar junction transistor. Under common emitter configuration. Emitter is common for input, output. Next, hybrid parameters. So the interrelationship of the here collector voltage, current, base emitter voltage, and base emitter current, which are the transistor characteristics. They have been slightly different values of the individual transistor, which are greatly from one type of transistor to the another here. So here to determine the relation of the input and output signals in a amplifier circuits, which can be used in the circuit, and whereas I see collector emitter volt current, which will be constant while base current is measured for various VC voltages. So the relationship between IC and VC, which is measured for other values, of base current, and these are called output characteristics. So the slope of the curve yields corresponding to transistor parameters, which is designated here as a given special monument um, because of their importance. These parameters can call it as a hybrid H parameters. Hybrid means H. So since the both impedance means input, the ratio of the here V by I, okay, V equals to IR, R equals to V by I. That you can call it as a here here conductance are considered here. So here the H parameters, since both impedance and conductance which are considered. So these are the what is output admittance here delta VIC by delta VCE with respect to base current constant. So that is H alpha, that is output admittance. Then other one is the HRE reverse voltage. Other is HFE forward current gain, and HI is the input impedance. Okay. So this is a HOE, not alpha. Print mistake. HOE output admittance. HI is input impedance. HRE reverse voltage ratio, and HFE forward current gain. Okay. Next is the configuration circuit arrangement for study of CB configuration, common base, how the hybrid parameters, input impedance, output impedance, forward current gain, reverse voltage. Yeah, just now we discussed the BJT, bipolar junction transistors. Through these slides, we have been discussed all these. Okay. PNP and NPN, common base configurations. We derived the equations also here. All these, where this equation This one beta is alpha by alpha, IC by IC. Okay, we have been derived these equations in PPT. These are the hybrid circuits. So this is very, very important. What is input out current here? So how you are going to represent the matrix representation? V1 equals to H11, H12, H21, H22. This is 2, H11, H12, H21, H22. Matrix representation with respect to V2, I2. V1, I1, V1, I2. Like that. Some mistakes are there, print mistakes. You can correct it. This one. How the H parameter values which are to be changing here for three different configurations: common emitter, common collector, and common base. Special semiconductor devices. Here FET is there, field effective transistor, tunnel diode, UJT, unijunction transistor, SCR silicon control rectifier is there, track and DAC, field effective transistor. So FET, which is a field effective transistor, which are voltage operated devices, like unlike bipolar transistors, FETs require virtually no input current, and this may give us an extremely high input resistance. And there are two major categories of FETs: junction FETs, JFETs, and IG FETs, that is insulated gate FETs. So these are further subdivided into P channel and N channel. What is the operating principle of the N channel means FET, which is illustrated by given below figure. A piece of N type material which may be referred as a channel, and which has a smaller piece of P type attached to its sides, and which is going to be forming a junction, PN junctions. And the channels ends which are designated the drain and the source, and the two pieces of P type material which are connected together to their terminals, which is called as a gate. Okay. So with this gate only, terminal which is not connected, and potential if it is going to be applying here, where which is positive at a drain, negative at a source. So the drain current ID, when the gate is in bias negative with respect to the source, the PN junctions are reverse biased and the depletion layer is going to be forming here. Since the channel is more lightly doped than the P type, the depletion layer penetrating deeper into these channels. Why? Because of here the depletion layer is region depleted of all charge carriers, either a positive holes or a negative electrons, and it behave like an insulator. So here the resistance is going to be increased. The drain current which is to be reduced here. Then the negative gate is going to be bias, and further if it is going to be increases, the depletion layer which is region which meets at the center. So here you can able to observe the diagrams for the here. This is figure A, B, C. No bias voltage, negative gate on, and which is here a small negative gate source and a large combining on. a separation, closely comes together and completely matching. So what are these? A tetrode connected. That means a source, gate, drain. D means drain, G means gate, S means source. Okay. So the figures, this is a tetrode connected here. 4 terminals, G1 and G2. Connected toward the source at the gate. This is the drain. This is opposite tetrode, other terminals. Which is showing that how the internal voltage drops along the channel, either P channel or N channel. How the resulting depletional region. Output characteristics as well as the input characteristics we need to discuss. Another one is the tunnel diode. This is the tunnel diode here. The energy bands is heavily doped here. In the PN junction diode, tunneling is going to be takes place. Two conditions. One is that under open circuit conditions, other one is with reverse bias, applied reverse bias. These are the conditions here. Characteristics and reverse bias as well as the forward bias. You need to discuss and you need to draw the diagram for that. Next is the UJT, uni-junction transistor, which is quite different from the BJTs. Only one direction the current may flow, that is UJT. BJT in either two ways. Okay. So FET is also a 3-terminal device. What do you have in FET? Gate, source, drain. So the input resistance of these devices, the device between emitter and base, which may be rapidly decreases when the input voltage reaches a certain volt level. And this is termed as a negative resistance. And it is this special characteristics which makes the UJT useful in designing several special circuits, like relaxation oscillators, timing circuit, RC. Okay. This is the basic construction of the UJT. This is the circuit area equivalent, symbolic representation of UJT means uni-junction transistor. SCR, silicon control rectifier. So, which can be thought of an ordinary rectifier of a control element. The current to the control element, which is termed by the gate, and which may determine the anode to cathode voltage at which the device commences to conduct, and gate bias may keep the device off, or it may permit the conduction to the commence at any desired point to the forward half cycle. So here the silicon control rectifier, which is widely employed a AC power control device. Okay, alternating current power control. Then other devices such as DAC and track, which are based on the SCR principle collectively, but SCR type device is known as thyristors. This term, which is derived from the thyratron and transistor, where thyratron is being a gas-filled tube which behave like a silicon control rectifier. So SCR sometimes referred to as a 4-layer device or PNPN device. So that which consists of 4 layers of semiconductor material, and alternatively p-type and n-type layer which is stacked. They are designated as a P1, N1, P2, N2. And how many junctions are there? There are 3 junctions. In BJT, 2 junctions are there, 2 diodes. Here, 3 junctions are produced. The junction may be produced J1, J2, J3. J3. There are 3 terminals. One is that anode, another one is the cathode, third one is the gate. Okay, this is the case. Silicon control rectifier. P1, P2, N1, N2. P1, N1, P2, N2. Junction J1, J2, J3. How many junctions? 3 junctions. P1, N1, P2, N2. P1, N1, P2, and between J3, J2, J1. 3 junctions are there. So 2 transistor equivalent circuit here. PNP, NPN, like that, 2 transistors. This is NPN, this is PNP. Okay, you can see PNP. Toward the base current is found from emitter to the collector, NPN. So what is the symbol is there? This one, anode, cathode, gate. Characteristics. Next, other most important repeatedly asking question is that track. So the equivalent circuit of track is which is going to be showing here. The device amounts to 2 inverse parallel connected SCRs with a common gate terminal. Okay, so here section N1, P2, N3, P3 form 1 SCR, which can be represented by transistor Q1 and Q2. Similarly, P1, N2, P2, N4. Another SCR which has the transistor equivalent circuit Q3 and Q4. So here P2 is the layer common to the both SCRs, and it functions as a gate for both devices. Because of the inverse parallel connections, other terminal cannot be identified, anode and cathode. Instead, they are designated A1 and A2. So when the gate is to be made positive with respect to A1 and A2, and also made positive with respect to A1, transistor Q3 and Q4, then switch it on. And so in this case, the A2 anode and the anode and the A1 is cathode, where the gate and the A1 which are made positive with respect to the A2. Q1, Q2 is switch on. A1 as the anode and A2 is the cathode. So that here you have to observe the track can be made to conduct in either directions, two-way directions. No matter what the bias polarities, the characteristics for the track are those of forward bias SCR. DAC is namely a track without gate terminal. So switching the device is affected by raising the applied voltage to the breakover voltage. So this is the symbol for DAC applications, VI characteristics. So by tomorrow's class, we will discuss about transistor amplifiers. In this transistor amplifiers, 4 units are there. One is the transistor biasing and load line analysis. Another one is the to know about the introduction of the amplifier and common emitter amplifier and also power amplifiers. Okay, completely amplifiers. What is transistor current components? Thermal runway, temperature related, fixed bias, self bias. This you can call it as emitter bias arrangement. BJT, how the BJT maybe works as an amplifier. Okay, this was already discussed in BJT. You can see here NPN and PNP transistor. Tomorrow I will explain through the slide. Thermal runway, most important. Expected short question is this. Thermal runway. Fixed bias, essay question. Self bias combination they are going to asking. Okay. How the BJT is and works as an amplifier. So by tomorrow's class, we will discuss about all these things. This one. Transistor biasing and load line resistance. Okay. I think so. You got an idea about that, how the questions are going to be giving out by the examiner, and how to. One thing you should remember that better to practice the circuit diagrams. Circuit is very, very important, and also whatever the concepts we are discussing, each and every concept is having what is input characteristics, what are the output characteristics. Okay, so. With respect to the graphical representation, you need to know about that what is going to be happening while you are going to using this circuit, what it will gives, what it not. Okay, how it works. So that structure is also important here. Symbol is also represented, important, as well as the here circuit diagram is also important. Okay. So by tomorrow's class, we will discuss transistor biasing and load line analysis. Okay, right, all the best. Thank you.